An electromagnetic wave has a magnetic field given by this equation. You need to figure out in which direction the wave is traveling, what is the frequency of the wave, and you need to write the vector equation for the electric field. Well, all we have to do is look at the magnetic field equation and compare it with a general one. And looking at this part, you have to realize that the magnetic field is traveling along the x-axis and it oscillates along the y-axis. Because the sign in the parentheses is positive, it means that the wave is traveling in the negative x direction. Now, what else does the problem give us? Well, from this equation we see that this is the maximum value of the magnetic field, so we know that the amplitude of the magnetic field is 8.25 times 10 to minus 9 Tesla. We know that the wave number k is 1.38 times 10 to the 4 meters to minus 1. And we can find the frequency as the ratio between the speed of light and wavelength, knowing that the wavelength is connected to the wave number by wave number k equals 2 pi over the wavelength. If we replace the wavelength with 2 pi over k, we have that the frequency is nothing else than the speed of light multiplied by the wave number divided by 2 pi. We know everything, all we have to do is replace the speed of light with 3 times 10 to the 8 and the wave number with 1.38 times 10 to the 4th divided by 2 pi. And we get that the frequency is 6.59 times 10 to 11 Hertz. Now, for the last part of the problem, we need to write the vector equation for the electric field. Well, that equation is very similar to the equation for the magnetic field, and it will be equal to the maximum value of the electric field multiplied by cosine of kx plus omega t, and we need to figure out the unit vector that we have to use here in order to show the direction in which the electric field is oscillating. Well, the magnetic field is oscillating along the y-axis and the wave is traveling along the x-axis. So clearly the electric field has to oscillate perpendicular to the magnetic field, which means it has to oscillate along the z-axis. It cannot oscillate along the x-axis because that's the direction of propagation. So all we have to do now is figure out all these constants so we can plug them in the equation. What we are missing is the maximum value of the electric field and the angular frequency omega. The maximum value of the electric field is related to the maximum value of the magnetic field. It's nothing else than C times B max. And if we multiply the magnitude of the magnetic field 8.25 times 10 to minus 9 with the speed of light, which is 3 times 10 to the 8, we get that the amplitude of the electric field is 2.48 newtons per coulomb. The angular frequency omega is related to the frequency of the wave as 2 pi times the frequency. And if we multiply the frequency, which we just found as being 6.59 times 10 to 11 Hertz, with 2 pi, we get that the angular frequency omega is 4.14 times 10 to the 12 radians per second. And now we can write the equation for the electric field. The electric field vector as a function of position and time will be equal to the maximum value of the electric field, which is 2.48 newtons per coulomb, multiplied by cosine of k, the wave number is 1.38 times 10 to the 4x, plus the angular frequency is 4.14 times 10 to the 12 multiplied by time, multiplied by the unit vector k.